Okay, now. Okay, so we have done elasticity, Abi. We have done calculations under force and under extension, and also we have done calculations under stress, under strain, and Young modulus. So today we're dealing with work done on a spring and elastic material. So this is a graph showing force against extension. I will listen now. So now we have P. So we have from O. O is the origin. P is the proportionality limit, and E is the elastic limit. Y is the yield point, and B is the breaking point. Now let me explain on this. Now, I explained some things during that first class when we were explaining Hooke's law. We said that Hooke's law said that what? What's Hooke's law? Okay, we said Hooke's law states that the extension produced by an elastic material is what? Directly proportional to the applied force, provided that the elastic limit of the material has not been exceeded. Abi? So everything that the law is just telling us is that the force applied is directly proportional to the extension. So it means the more you apply force, the more the material extends. I'm using this diagram to explain that Hooke's law. So we have this. We have a material. This one here is a spring. Is a spring. So this one is the elastic material. We have, in that case, so we have this. 1, 2, 3, 4. Okay. And so we attached a mass. The mass is being attached, and in that case, let's call here our M1. So this is the original length for the spring. From here to here is the original length of the spring. Here is the length of the spring. So from here to here, that is the original length of the spring. So from here down to here, this is the extension. This is the extension. Let's call it extension 1. However, in that scenario, we have this, we have this, we have this, we have this. Let me bring this a little bit up that the video that the phone can cover it. So we have 1, 2, 3, 4, 5. You see here we have this. We have the bigger mass. So here where we have. Let me extend this so we have a bigger mass here. See, we have a bigger mass. Yes, from here to here is our extension. So it's our original length of the material. This is the length of the material. So from here to here, this is the extension. Let's go here E2, let's go here M2. So from Hooke's law, we said Hooke's law states that the extension produced in an elastic material is directly proportional to the applied force, provided that the elastic limit of the material has not been exceeded. So the law is saying that force is directly proportional to applied force, and extension is directly proportional to the applied force. It means, okay, from here we now have we introduce constants, and change this kind of proportion to equal to. So you have Ke, where K is spring constant, elastic constant, stiffness of the spring, and so on and so on, like force constant and so on. So we said that from Hooke's law, we said the more the force, the more the what? Extension. So if I apply force here, or I apply mass here, there will be what? An extension, If I apply a bigger force, or apply a bigger load, or a bigger mass, there will also be what? A bigger what there? Extension. So the higher the force, the higher the what there? The extension. So that is what Hooke's law is trying to tell us. So now from here, we have the graph of force against extension. So this is the origin, this is the proportionality limit, E is the elastic limit, Y is the yield point, B is the breaking point. So we have from O to E is the elastic region, from E to B is the plastic region, and B is the breaking point. Let me explain what this means. Now this P here. Now if I apply force to a particular elastic material, it will extend, Now this from here to here is the point where whereby if I apply force, it continues to extend. If I apply force, it extends. If I apply force, it extends. So what happens is that the extension increases with what? The increase in what? With force, So from this proportionality limit, we move to the elastic limit. So this elastic limit is the limit where if I apply force, a point will come that if I apply force, the particular elastic material can no longer extends. Can no longer extends. If you kind of drag a rubber, or let me say a plastic or a spring, if you drag it, you apply force to a point that particular spring or rubber can no more extend. The limit has been exceeded. So you have gotten to the elastic limit. So this is the elastic limit here. Now, when remember, it goes from the origin to the what? Proportionality limit. Then from there to the what there? Elastic limit. Now, when you apply more force, a point will come that particular substance can no longer go back to its original shape and size. For every elastic material, if you remember, we define elasticity as the ability of a material to do what? Regain its original shape and size after it has been distorted by force. Abi? So that particular material, no, we furthermore said that provided, in Hooke's law, we said provided that the elastic limit has not been exceeded. Abi? That the more you apply the force, the more the material will do what? We extend. Abi? Now, from those two concepts now, think about this point that if I continue to apply force to a particular material, it goes from its extending, and if I release that particular material, I can go back to that original shape and size, abi? So I can regain that size and shape, abi? If I continue to apply force, it gets to a limit where it can no more extend, abi? That's the elastic limit here, abi? Now, if I now continue to like apply force, because we come to that particular material will now become plastic. We call it plasticity. Like can no more go back to the original shape. It becomes like plastic. Can no more go back to its original shape. Become plastic. It will just be like can no more, like it's not elastic. It's not elastic. It's just there. It's just like, we call it plasticity. That's the property there. So you can no more go back to that original shape and size. Alright, so that's the yield point there. That's the yield point. So this point is the point where that particular elastic material becomes plastic. This is very, very well low. It goes from the what? The origin to the what? Proportionality limit. This point here, if you apply force, it extends. Apply force, it extends. It goes then to what? Elastic limit. That is, at this point here, it can no more extend. The limit has been gotten to. The limit has been gotten to. And it goes from here to what there? If you want to apply force, it goes to where? The yield point, where it becomes plastic. Where it becomes plastic. So this is, so it goes from that yield point to what there? The breaking point, where it finally snap or cuts. If you apply force. So that is where this Hooke's law now makes sense. It says that if the elastic limit has not been exceeded, the applied force is what? Direct to the extension. It means the more you apply force, the more the extension, until the elastic limit is what? Is exceeded. If you apply force, it extends. If you apply force, it extends. In as much as that elastic limit has not been gotten to. If you apply force, it will extend. If you apply force, it will extend. In as much as that limit has not been gotten to. So if that limit is being gotten to, it can no more extend. Can no more extend. And if it extends, it becomes plastic. From being plastic, it does what there? It breaks off, it snaps off. Okay, with that being said, from this graph here, we have this. Any question here? Alright, we have from O to E is the elastic region. From E to B is the what? The plastic region. And B is the what there? The breaking point. Alright, from here we have this here. I can sketch this one from here like this to this force axis, which is the y axis or the axis. And I can bring it here. So taking this side, we are going to have this. We're going to have this. Let me bring it down a little bit. We're going to have this. This is force. Okay, this is force. Let me bring it closer. This is force in Newton, and this is the extension. This is the extension in meters. So bringing this idea, we're going to have this, So you have this. So this particular region is what we refer to as the work done on a spring. The work done on a spring. Work done on a spring. Remember the idea for work done. We said work done. Work done normally work done equals to what there? Force times distance. Have you? Now remember inside work done, there's this concept there that even though you apply force and there's no distance, work done is zero. I will listen now. And by just push this body, by kind of apply force to this body and it's not moving, work done is zero. In as much as there's no movement, there's no movement. So even if I apply force of 15 Newton, and the distance is zero, what happened there? The work done is what there? Zero. So no work done. So no work is done. So in the case of work done on a spring and elastic material, this is the graph of the force against the extension, against the distance. Okay, now. So this is the idea under work done on a spring and elastic material. Okay, that being said, alright, let me use this. Alright. So in the case of this graph, we said work done equals to area of graph. I will listen now. What do we say? We said what there? Work done is what there? Work done equals to the area of graph. Work done is area of graph. Now, okay, we said work done on a spring or elastic material equals to what there? Area of graph. Area of graph. Now, if we check this shape, it is a triangle. Abi? Now, so we can say work done equals to the formula for triangle. Area of triangle is what there? Half base times what there? Times height. Abi? We said work done is equals to area of graph. Abi? And the area of this graph is a triangle. And area of a triangle is half base times height. Abi? Okay, with that being said, we have half. Our base here is this our extension here, Abi? And have our extension times our height, Abi? Our height here is direct to what there? Is for the force, Abi? So we can have force here. So we can write this as work done equals half multiplied by force multiplied by extension times extension. So can I write this as this? You see the same thing. So can I write it as this. And let me point something out again. Let me remind you of something. When we're stating Hooke's law, we said that the extension produced in an elastic material is directly proportional to the applied force. Abi? That law we follow it word by word. You can see that the extension is direct to force, to the applied force. Abi? And I said it's not correct to write it this way, but instead be written like this. Because the idea is that if there is no force applied, there is no what? Extension. So force has to come first before there can be an extension. If I don't apply force in a particular elastic material, cannot extend. Abi? So force has to come first before extension. And the same thing applies for Ohm's law. We still get on that. So we have, but it's not the idea for this. So I'm only writing this like this. So you can do it this way or this way. See the same thing. I'm only just doing some kind of revision on that. Okay. Now remember, let's recall from Hooke's law, we have force to be like F equals to Ke. Is that not so? Abi? We have force equals to Ke. No, he said force is the rate to extension, Abi? And we said force to remove this sign of proportion when we do what? Introduce constant, Abi? We introduce constants, and we have this. So we have this. So let's record that force equals to spring constant or force constant or stiffness of a spring multiplied by what? The extension. Abi? If this is true, we're going to have work done on a spring to be equal to half multiplied by my force here. My force here is now what? The spring constant and what? The extension. Abi? I'm going to have Ke, Abi, multiplied by what? The times E. Abi? If that is true, my work done on the spring goes further to become 1 over 2 multiplied by what? The Ke squared. Abi? Is that also? Alright. So you can call this one, let me call this one my equation 1. Let me call this one my equation 2. Equation 2. Okay. Now, one more thing. Let's not forget, if force equals to spring constant times extension, if I make this extension to stand alone, I'm going to have F equals to Ke, Abi. I can have Ke and have Ke. Ke cancel Ke, Abi. So I can have my extension to be equals to force over spring constant, Abi. Now, if I apply this idea into equation 1, I'm going to have my work done to be equal to half multiplied by the word there, force, Abi, multiplied by my extension is now what? Force over what there? Spring constant, Abi. So I can just substitute my extension here with what? Force over spring constant. So I'm going to have force over spring constant. So, and that implies that my work done on the spring, it will be equal to 1 over 2 F squared over what there? Over K. Abi? That also? Am I correct on that? So this one can become my equation what there? Equation 3. So these are the equations we have. Under work done in the spring or an elastic material. So can you use any of this equation? to solve questions when dealing with calculations under work done on a spring. So let's solve some examples and then we proceed. Let's solve this. Question 1 now. A spring is stretched 40 millimeter by a force 15 Newton. Full stop. A spring is stretched 40 millimeter by a force 15 Newton. Full stop. What is the work done by the force? What is the work done by the force? Let's solve that. Solution. Now, as usual in physics, if we see any question, the first thing to always do is to state your parameters. That's the first thing to always do. In that question now, what parameters are we given? We are given force, Abby. Force will be what there? 15 Newton. What again are we given? We are given the extension, Abby, as what there? As 40, Abby. 40 millimeter, Abby. Okay. And what's the question? What is the work done, Abby? So work done becomes question mark, Abby. So very simple. Our first task here is to convert from millimeter to meters, Abby. Now listen very well. In your question, listen. In your question, if the options are in millimeters per Newton, don't need to convert. Don't convert. Don't convert. So if it's in meters, then you need to convert. But in most cases, there is need for conversion from millimeters to meters. Alright, that being said, converting from 40 millimeter to meters, that will divide by what? 1000, Abby. Alright, so we're going to have, let's say you have 40 divided by 1000, 0 cancel 0, Abby. So we're having 4 about 100, Abby. How many 0 do we have here? Just 2. Just 2 0. So it means we are going this side twice, Abby. So it becomes 1 and what there? 2, Abby. We're going to have 0, another 0 here, Abby. And then it becomes point. So we have what there? 0.4 there, 0.04, Abby. Okay. So we're going to have 0.04 meters. 0.04 meters. So now let's recall, work done equals to what there? Half what there? Half force times what there? Extension, Abby. Half force times extension, Abby. Alright, our work done on a spring now equals to 1/2. Our force is what there? 15 Newton, Abby. And the extension is what there? 0.04, Abby. Okay, now let's press calculator. What do you have there? Work done now equals to what there? What do you have? 15 times 0.04 give us what? 15 times 0.04 give us what there? 7.6. 0.6 over 2. Okay? Work done becomes what there? That's 0.3, Abby. So 0.3. That's what there. Work done is in what? Is in joules, Abby. Is in joules. It's in joules. It's in joules. Okay. If you 15 years in Newton, Abi. Yes, meters, Abi. You got be Newton meter, Abi. Okay, that's joules. Alright. Any question here? Any question? Yeah, I'm listening. It's only joules. It's only joules. We can put it also in Newton meter. Can put it as Newton meter. I will listen now. You know, under this thing, what's it called there? Under power. You know, power is what, Abi? You know, power is what? That also. But another unit for watts, I mean for power, is also joules per second. Have you listened now? But we use what there? Watts. Abi? Same thing also applies for this thing there, for current. Current is a coulombs per second. But we use what there? We use what there? We use ampere. So that's the fact there. Any other question? Alright, question 2 now. Question 2. A spiral spring is compressed by 0.02 meter, full stop. A spiral spring is compressed by 0.02 meter, full stop. Calculate the energy stored in the spring. If the force constant is 400 Newton per meter. A spiral spring is compressed by 0.02 meter. Calculate the energy stored in the spring if the force constant is 400 Newton per meter. Okay. Okay. How are we giving? I'm giving an extension to the word there. 0.02 meters, Abi? The meters? Okay. What thing are we giving? We're giving what there? Force constant, Abi? That is what there? K. As what? 400 Newton per meters. What thing? Is that all? Energy stored, Abi? That is the work done. That's the work done over there. Okay, now let's check here. Best formula to make use of here is what? Second equation, Abi, or first one or third one? Second one, Abi. Okay. So let's work done equals to what there? Half force constant extension square, Abi. Okay, that being said, what equals to 1/2? What's force constant there? 400, Abi. Multiplied by what our extension? 0.02 squared, Abi. Okay. Okay, let's multiply it. What do we have? Let's trace it. What do we have? Work done equals to everything over 2. What do we have here? What do we have up here? 400 multiplied by 0.02 squared. What do we have? We have 0.08. $400, okay, 0.02 squared, what do we have? Mm-hmm. 0.004. This squared. Are you sure 0.04? Are you sure? 0.004. Abi? Yeah. Times 400, what do we have? 0.16, Abi? 0. Not 16, no, 16. 0.16. So finally, I worked out the cost word there. 0.8 word there. Joules, Abi? Alright. Any question here? Now let me give you last hope. So you can call it a day. Not a day as in, for the video, a day. Now let's solve this. Now let's write. A spring of force constant. A spring of force constant. A spring of force constant. 1,500 Newton per meter. Is it correct? 0.08. 0.08 joules. Yeah. A spring of force constant 1,500 Newton per meter is acted upon by a constant force. Is acted upon by a constant force. Is acted upon by a constant force of 75 Newton. 75 Newton. Calculate the potential energy in the string. Calculate the potential energy in the spring. Calculate the potential energy in the spring. Yes. So what they are asking there, you can see them asking to find work done. They ask you to calculate energy stored in the spring, or calculate potential energy. In the case of spring, it seems same thing as work done. How will you see now? So they ask you to calculate work done there. Exactly now. So now, if you define your parameters, what are we giving? By giving what? Force constant, Abi. And what again? Force, Abi. Force is in Newton, Abi. And force constant is in what? Newton per meter. So it's two different things, Abi. So now what's the best formula to make use of here? Third one, Abi. Alright, so solve the answer and give me your and you can solve the question and give me your answer. Okay. That'll be all under work done on a spring.